Hello, everyone. I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Trinh, who is I think just finishing at NYU and at Google Deepmind. And he'll talk about a famous work, AlphaGeometry, that solves IMO level geometry math problems at the level of a gold medalist. So as I always do, I'll watch the chat, and if you have questions, you can put them in the chat, and I'll either encourage you to go ahead or relay them to Trieu. And you'll take questions as well during the talk, and we'll have a few minutes for discussion at the end. So with that, please, Trieu, begin.
All right. Is everyone seeing the slide, right?
Yes. Yep.
Okay. Yeah. Hi, everyone. My name is Trieu, and this is a joint work with Tony, Kwok, He, and Tang. So let me start out by some inspiration that we have at the beginning of the project. So many years ago, I've learned that there's this Fermat's last theorem that says something very simple. That is this very simple equation that does not have any solution. And even though it is so simple, it turns out that it took humans hundreds of years to solve the problem. Many people getting involved and going down different paths, but somehow along the way, some mathematician becomes interested in studying elliptic curves and modular forms, which turns out to have very deep connection with the original question. And so they use this new angle and solve the problem eventually. So this is a wonderful story about human intelligence, but also at the same time, it made me wonder, how is it possible, or what are the principles that allow humans to do this? And how do we even build a computer for this? So that next time when we ask such a difficult question, we don't have to wait for hundreds of years, but probably 20 or 30 years running a GPU or TPU cluster is good enough. So what we, obviously this is a very big question. I don't think we made any progress on it, except for the fact that what we managed to build is some sort of a proof of concept for an answer for a toy version of this original question. And the toy version of this question is, how do we even solve the problem at the International Mathematical Olympiad, also known as the IMO? So the good thing about problems at the IMO is that they are known to be hard questions, but not too hard, because you always have this guarantee that a well-trained human can figure out the solution within a few hours. So it is a good benchmark to target. Also, at the same time, it is considered a grand challenge for computer reasoning, because at the moment, the computer capability is still far below human level. If you take GPT-4 or any other theorem-proving machines, it's likely that their performance is far below human level. So fortunately for us, when we look at geometry, it turns out that all the conditions are just right in such a way that we can build this proof of concept answer that significantly narrow down the gap between human and machine for geometry. So this talk, I'll describe exactly what the solution is and what are the conditions that allow us to do this for geometry. So let me proceed by presenting three of my favorite examples of the kind of questions and solutions that tends to appear at the competitions. And then together we'll make some observations about what are the hard things about solving these problems and what are the easy things about solving these problems. And then from these observations, we'll build our solution. Okay, so first example, this is an example in number theory where the question is how many primes are there? I guess all of us here know that there's an infinite number of primes, and the proof would go roughly like this. So the proofs start out by assuming otherwise, which is there's only a finite number of primes from P1 to Pn. And then Euclid, who is a mathematician living many thousand years ago, would suggest that we should construct this new number P as the product of all of these primes and then add 1. And by this construction, this new number is not going to be divisible by any of the primes. And so by definition, this is a new prime missing from the original list. So we have a contradiction, and they have to have an infinite number of primes. So this is a very classical, famous proof. But I want to point out that this blue line that I highlighted in the proof here seems to be the genius part of the proof. Because by constructing this new number, Euclid managed to do something that I guess many mathematicians nowadays call pulling the rabbit out of the hat, which is why I'm placing this rabbit icon over here on the right. The remaining part of the proof is relatively more mechanical. And so with this example, I'd like to introduce you to the first important concept in our work, which is the rabbit. Second example, let's say this time we want to solve an equation, 4 to the x plus 9 to the x plus 1 equal to 6 to the x plus 1. So this solution is really scary to me, at least, because my mathematical training probably stopped around high school, where I only know how to solve a quadratic equation because there's an easy formula to follow. But this equation is very strange. But at the same time, back in high school, I also have this very clever friend who would, just come along and look at difficult problems like this for a few seconds and suggest something like, let's try y as 2/3 to the power of x and see what happened. So what ended up happening is that this original equation becomes something that I'm very familiar with, which is a quadratic equation. So now I can just follow my routine formula and derive all the way to the final solution. And in fact, one can imagine that you can use there's multiple mathematical software nowadays that can just automate this part of the proof, this part of the solution. For example, Wolfram Alpha wouldn't have any trouble solving for x. So with this second example, I'd like to introduce you to the second important part of our work, which is the symbolic engine. The role of the symbolic engine is to encode all of these familiar cases and all these mechanical problem-solving skills and implement that really efficiently. With that, let's move on to the last example. This time we look at geometry, which is the focus of our work. So in geometry, what you are usually asked to do is to first construct a bunch of points and lines. So in this case, for the IMO 2018 problem 1, we're asked to construct A, B, C, and then D, E, and then F, G according to some formula. And then once we finish constructing this diagram, we're asked to prove something that happened. In this case, we're asked to prove that these two red lines are parallel. And I have no idea where to start with, where to even begin with this problem. I'm not even qualified to be at the IMO. So let's borrow my clever friend again, who would come along, look at this problem for a few minutes, probably play with it for a while, and then come up with something like this. How about we construct this point M at the midpoint of arc AB and N as the midpoint of arc AC, and connect them and see what happened. So what happened is that I still don't know how to solve this problem because this didn't become a quadratic equation. But fortunately for geometry, we actually do have a symbolic engine that can finish this proof within just a few seconds or up to a few minutes, as long as you gave the symbolic engine these two rabbits. And in geometry, we also call the rabbit magic instruction or auxiliary points and lines, which is the terminology that people tend to use during high school. In the paper, we also presented some other examples, one in tiling a graph or another one in solving an inequality problems at the IMO. And both of these examples exhibit this rabbit and symbolic engine structure. So I guess at this point, I guess everyone get the point, or rather the general observation is here is that given a problem, what we would usually do is we come up with this magic construction, and then with this magic construction, we probably would be able to transform the problem into a state that is easier to solve for the mechanical solver. And then if the mechanical solver failed to solve this problem, then we can always come back and ask for more rabbit, and then we keep running this loop, these two components in a loop until we get the solution. So this is the general observation, and what we ended up building the solver in our paper mimic exactly this structure, where we try to train a neural language model that can come up with the rabbit in such a way that it can help the symbolic engine for geometry to solve the problem. And then we put these two components into a loop, and hopefully we'll get the solution at the end. Before moving on, let me clarify one point here, which is this observation of a neuro-symbolic structure is not a new one. At least back in 2020, there's a paper from Polu and Suskever which is also the first paper that have brought language model into theorem proving. They have already made the observation that a major limitation of automated theorem provers compared to human is the ability to generate original mathematical terms, which is the rabbit. And this limitation might be addressable via the generation from a language models. And so with the context of this work, the observation that we have made is not new. The new thing here is that we don't have the human annotated data to train the language model in order to come up with the rabbit. So we have to solve the problem of generating the synthetic data. Moving on, the remaining part of the talk, I'll make it really clear what are the input and output of our solver, and then I'll go into describing the two components, which is how do we build a symbolic engine, and how do we even train a language model that can come up with a rabbit. And then I'll wrap it up with some results, analysis, and some discussion. So first of all, what are the input and output of our solver? Going from left to right, the input of our solver is a geometry problem stated in natural language. And the first thing that happened is that there have to be me who step in and manually translate this natural language into a domain, a geometry specific language that computer can easily parse and verify. And then once we have this intermediate representation, we can just feed it into AlphaGeometry, which is the solver that we built, which is also the neuro-symbolic loop. We run it in this loop, and hopefully at the end, we return on the other side a solution to the original problem. And this solution is also in the geometry specific language that we can easily parse and verify automatically. But because this language have a very natural grammar to read, so we also have the option to manually evaluate this solution by consulting some expert, that just like the way human solutions are evaluated at the IMO. And in our case, we submitted four of our solution in the year 2000 and 2015 to Evan Chen, who is the coach for the IMO team of the US, for an evaluation. And we get a full score for these four solutions, meaning we get enough points to win a bronze medal in these 2 years. So this is the input and output of our solver. Let's now look at the two components of the solver. The first component being the symbolic engine. The name of the symbolic engine is DDAR, which stands for deductive and algebraic reasoning. And this symbolic engine have two parts, which is highlighted in these two boxes. In the first component, which is the deductive reasoning part, the symbolic engine would just follow a list of predefined rules in order to derive new fact so that it can find the final conclusion. So this list of rules is already collected in the previous work, and the way the efficient algorithm to follow this list of rules to derive new facts is also a solved problem in the previous work. And just to read out loud one of the rule here. So at line 7, we have the rule saying if E is the midpoint of AB and F is the midpoint of AC, then EF should be parallel to BC. So this is an example of one rule. And the contribution in our work is that we realize in a lot of IMO geometry solutions, we also have to a lot of time do algebraic manipulation of angles or ratios or distances between points. And these algebraic manipulation, which is shown on the right here, is not covered by the deduction rules on the left. And as it turns out, a process similar to Gaussian elimination can capture all of this algebraic manipulation. And I won't go deeper into the detail, but the symbolic engine DDAR essentially is a combination of these two parts. And when combine these two together, we already get a pretty good geometry problem solver. And how good is it? Well, when tested this symbolic engine DDAR on a set of 30 geometry problem, that is Olympiad geometry problem, that is taken from the IMO between 2000 and 2022, DDAR can already get 14, which is already stronger than the previous state of the art. However, 14 is still very, very far from the top human performance on this set, which is 26, which is the average number of problems solved by the gold medalist. And 14 is also even lower than the 14.3, which is the average number of problems solved by honorable mentions. And the reason why we have such a big gap is because no matter how strong we try to build this symbolic engine, there's still one key missing ingredient in our work that human is really brilliant at doing, but not so brilliant at explaining exactly how to do it. And that is exactly coming up with the rabbit. And at this point, we see that now it is time to bring in machine learning and the power of learning from data. And then we train a language model to come up with the rabbit and put it together with a symbolic engine. And we were able to bring the final result to 25, which is somewhere between silver and gold medalists. Just to make it really clear, this benchmark is only on geometry. but the IMO also also include 3 other domains of mathematics. And so 25 is just on geometry. So the final question here is, how do we even train a language model to come up with a rabbit? And I guess the first question whenever we talk about training a language model is, where do we even get the data? And in our case, as I mentioned earlier, we don't really have the data to train the language model to come up with a rabbit in such a way that it can help DDAR. And so we have to come up with a way to generate this data synthetically. And this way is shown in this slide. We have these three very simple steps in order to generate synthetic theorems and proofs. In the first step, what we do is sample a bunch of random mathematical facts. For example, let's say we sample A equal B and B equals C. And then in the second step, we do deduction, where we refer to the list of rules, the deduction rules, and see based on what rules we can apply in order to deduce new fact from this original set of fact. So in our case, A equal B and B equals C, we can deduce A equals C thanks to the rule of transitivity of equality. At the end of the second step, what we ended up with is a tree with 2 leaves and 1 root. In the third step, what we do is to serialize this tree into a string. And the way we serialize is as follows. We say theorem, and then we list all the leaves, which is let A equal B and B equals C. And then we say we want to prove the root at A equals C. And then the proof would be just describing exactly how do we connect from the leaf to the root. And the proof here is then just applying the transitivity of equality on A equal B and B equals C. And once we have this the string, then we can train a language model on it. A quick note here is that even though what I'm showing here is the string being in natural language, what we're working on is a language that is geometry specific. I guess this is a good point to pause and see if there's any question.
Yeah, I'm not totally following. So you sample a collection, basically a statement, and then you know what deduction is being made? I mean,
yeah. So in the second step, what we have is a random collection of mathematical facts.
right,
What we also have is also a list of deduction rules
right.
that is given. For example, geometry, you have such a list. And then we try to see, applying these deduction rules, we try to see what new fact we can deduce from this original list of facts.
So you just basically expand the whole possible deduction tree to some depth, and then how do you choose what's an interesting deduction or which deduction is? So you've chosen well, in this case, there's not very many, but in general, there would be many possible deductions. Do you try to take all of them?
Yes. So in the general case, we have a deeper tree and a larger number of leaves, right? What
Right.
we ended up doing is just taking all the derivative nodes, and each of these nodes would correspond to a theorem.
Okay. So you train basically on random set of facts, random sequence of deductions of some, distance in the tree, and then that's the training data. That's okay.
Yeah, that's exactly.
Okay, so
exactly
it's not selected in some further way. It really just is a kind of okay. Thanks.
Yeah. Yeah. So since there's no other question, I do have a question for this slide, which is originally when I when I motivate the use of the language model, it is used for generating the rabbit. And what we're looking at here, there's no rabbit.
I just got one question on the chat is, would
Yes.
taking the axioms in your examples, B equals C and A equals B in the other order, would that have counted as a different derivation?
Uh,
So in other words, you had the implicit choice of, transitivity takes
oh,
two
I
arguments
see.
and,
Yeah, so we try to account for that equivalence of proof as well in the later step where we deduplicate between these proofs.
right.
Yeah, so we try to account for that too.
Okay, so some symmetries are accounted for.
Yeah.
Okay, thank you.
Yeah, so currently what I'm seeing in this proof is that I have not seen any rabbit, in the sense that I'm not constructing anything new, any new variables. And this is this recipe is not the full recipe in our work. But before moving on, let me point out that even this recipe of generating theorem synthetic data to train theorem prover is not new. At least in the work in 2021, the author have also trained a theorem prover based on purely synthetic data. And there's a quote from this work that is, there is a class of theorems that this algorithm cannot generate. That are the theorems that introduce new symbols, new axioms, and hypotheses. So this is exactly the rabbit. So again, the recipe that I presented in the previous slide have not been able to generate rabbit. And here comes the core contribution of our work, which is we figure out a twist to this recipe that allow you to generate this rabbit. And in order to show that, let me go through these 3-step recipe again, but this time we'll look at a slightly larger example. And let's say in the first step, we managed to sample these 3 random facts of AB equal AC, DB equal DC, and DBC are points on the same lines. And you can look at this in the diagram on the right here, where we have this triangle with 2 equal sides and D being the midpoint of BC. So now with these 3 random facts, what we do is, again, refer to the deduction rule list in geometry, and we managed to build this slightly larger tree where we have one intermediate node before we derive the final node. And the final node here at the root is saying that angle ABC is equal to angle BCA, which is represented by the 2 gray angle at the bottom of this triangle. And once we have this second step where we finish building the tree, we would serialize this tree into a string, just according to the previous recipe, where we start out by saying theorem, and then we list all the leaves. And all the leaves here are saying that there is a triangle with 2 equal sides and a midpoint, and we want to prove the root being the 2 angles at the bottom are equal. And then the proof here would have 2 steps, where the first step we have to introduce this intermediate result before using it to derive the final conclusion. So the proof have 2 steps. So far everything is still the same, but there's something special going on. The special thing being D being the midpoint of BC. So there are 2 special things about it. First of all, D being the midpoint of BC is actually unnecessary to state the theorem, because as long as this triangle have 2 equal sides, it should have 2 equal angle. It doesn't matter whether that triangle have a midpoint or not. And then the second special thing about D being the midpoint of BC is actually it is necessary for the proof to work. And the reason why is because D being the midpoint of BC correspond to the second and the third leaf, which are necessary to connect the first leaf to the final conclusion. And so we cannot just throw D being the midpoint of BC out of the picture. What we ended up doing in our work is we move this part from the problem statement to the proof and obtain a new theorem and obtain a new synthetic theorem and proof. And this time the theorem is, given a triangle with 2 equal sides, we want to prove it has 2 equal angles. And the proof would start out by constructing D as the midpoint of BC, which is exactly the rabbit that we're looking for. And here's also a good point that I should pause and see if there's any question.
Question. Can you hear me?
Yes.
So is there just this one rabbit that's being generated, or is the language model generating lots of rabbits that you use trial and error to weed out the ones that don't work?
In this way of generating synthetic data, we have not used any language model. So that's the first thing. The second thing is that in this way of generating synthetic data, we might be able to find a lot of rabbits. And so if we generate a lot of rabbit in one single synthetic theorem and proof, then the language model would learn to generate all of them. Does that make sense?
Yeah.
Now, in your example, if I combine this with what you were saying before, this comes by sampling to get these 3 statements on the top line and
Yes.
running, your deduction and then looking at the result and seeing that you can extract out this, as you say, rabbit. Okay, so
Yes.
really just sampling. There's not like a guided process for searching for these things,
No.
but the random process does produce enough useful rabbits.
Yes.
Okay, thanks.
Which might not be true for other domains of math, but
Right.
at least for geometry, what we found out is this is a core piece that allows us to get good data.
Right.
Which might not be true for other domains of math. Yeah, so so far, just to highlight, just to stress again, this recipe has not been using any language model, AI, any guidance, nothing at all, just random and then procedural generation of synthetic theorem and proof. So I do have a question for this slide also, which is, how do we even identify this blue part to be the rabbit part? So we sample a bunch of leaf and we build a tree and so on, but how do we point to this blue part being the part that you can move from problem statement to the proof? And in order to answer that question, there's also a 4-step recipe, where in the first step, of course, we have to build the tree. Given the 3 random leaves, we build the tree. In the second step, we do something called conclusion traceback. Essentially, we look at the conclusion and see which leaves are necessary for the conclusion to work. Essentially, we follow in the opposite direction of all these blue arrows, and we get this set of 3 leaves that are necessary for the conclusion to work. We call this DC. And then in the third step, we also look at the conclusion, but this time we only look at the objects that are presented in the conclusion. So in our case, this is A, B, and C, and also the angle ABC and the angle BCA. And we ask the question, based on which leaves are those objects constructed? And so these objects are only constructed based on the single leaf, AB equal AC. And finally, in the last step, we subtract these 2 sets and we get these dependency difference. That is the second and the third leaf, which is exactly the rabbit that we're looking for. So with this 4-step recipe, this is essentially all of our paper. I want to highlight that on the first look, it seems that this recipe seems to be pretty general, because all that we're doing is sampling fact, building tree, doing the traceback. it seems to be applicable to other domains of mathematics too. But in order for us to make this to work for geometry, we ended up having to do a lot of things that is specialized for geometry. For example, even before any of this that happened, we have to have this geometry specific language to describe geometry. We have to have this list of deduction rules, which is a solved problem from a previous work. And then in order to build a tree very efficiently, we have to build the symbolic engine, DDAR, that is very specialized for geometry. And then in order to do all the traceback, because we built the tree using a specialized solution, tracing back along this tree also requires a bunch of specialized solution. For example, finding some minimum spanning tree or solving a linear programming problem, and so on. So we don't want to give the false impression that this can easily be applied. There's a lot of specialized solution that we ended up building to make it to work for geometry. And with that, we already have all the recipe necessary to generate as much data as possible. And the only thing left to do is to scale up and generate as much data as possible. So here is a random sample of 12 diagrams. And each of the diagram here would correspond to one random setup leaf that we sample. And once we sample such a random setup leaf, we can construct this diagram, and then we can construct the tree, and then we can extract from there a bunch of proof. In terms of numbers, on average, we sample up to 60 leaves per diagram, and then we run this process massively in parallel over 100,000 CPU workers over many days. And at the end, when we serialize the tree into the proof, we also try to account for the equivalent of the proof. And after deduplication, we get around 100 million theorems and proofs. And how do those theorems and proofs look like? And here's what they look like. In this chart, this is a histogram of the proof length or the tree size that we generated using the recipe. And as you can see, most of the proof concentrated on the left, meaning most of them are pretty short. And just to compare with the proof length that we found on the test set of the IMO problems, the average IMO problems proof length is around 50 over here. But the synthetic data that we generated also cover a very large coverage of proof length all the way out here at nearly 250 proof steps. And just to give some examples, if you look at the proof that is generated that has only length equal 1, then we see some very trivial theorem. For example, if we have these two right angle, then these 4 points should be on the same circle. That is 1. And then when we look at the proof that have length between 20 and 30, we found a bunch of very well-known Euclidean geometry theorems. For example, this theorem is an Euler circle theorem. And all the way out here, the longest proof possible that we found in this case is this very messy looking theorem, where the theorem essentially asks to construct a bunch of points and lines, and then ask us to prove that these two blue angles are equal. And in order to prove this theorem, it turns out that we also need to construct two rabbits and follow that up with more than 200 proof steps to prove this theorem. And overall, out of the 100 million synthetic theorems and proofs that we generated, 9% of them are with the rabbit, and the remaining 91% of them are pure mechanical proof step, meaning DDAR can just solve these problems on its own. And what we ended up doing is we pre-trained from scratch a small language model from random weights on all of the 100 million synthetic theorems and proof, and then fine-tune it again on this small slice of synthetic proof that involved rabbit. And then finally, once we have that language model, we put it into this neuro-symbolic loop that I presented, and then try it on the test set. So the result you already know. We get a pretty good geometry theorem prover, and it outperformed previous state-of-the-art result, and also significantly closing the gap between human and machine. In our paper, we also have a bunch of other quantitative and qualitative analysis. But I like to highlight here some of the important points. First of all, when we look at the proof that is generated by AlphaGeometry, all of the proof steps are based on very low-level deductions. And that is because the list of deduction rules that we use is very low level. And this is very different from the way human write proof, where a lot of time we use a lot of intuition and high-level theorem to make a lot of deduction very fast. So what we ended up with is very long proof, very hard to read, but according to the Olympiad expert who do the manual evaluation of the proof, these proofs have really no soul, because we don't really have no idea what are the core key steps in this 200 proof steps, and what are the less important steps. So that is the first thing. The second thing that we observed is that at 20% of the training data, meaning around 20 million training samples, we already solved 21 problem out of 30, which is 80% of the performance that we have achieved on the using 100% of training data. So what we're seeing here is a diminishing returns when we try to generate more and more training examples. And part of the reason might be because the training data that we are generating is completely random, and there's no guidance towards hard problem or interesting problem, and we might ended up with a lot of uninteresting problem that does not help at all with solving IMO problems. And in fact, when we look at the more into the 100 million training data, most of the training data is very uninteresting. For example, this most complicated proof is completely uninteresting to a human reader, just because of the fact that it does not look clean, symmetrical, or the fact that these two blue angles are equal is also not that interesting. And so I guess the remaining question in our work, which we might look into in the future, is how do we capture this notion of interestingness in the synthetic data generation? But I do have some slides to discuss that. But at this point, maybe I should pause and see if there's any question, because this is already the end of the paper.
Yeah, thanks. Just to be a little bit more detail. So this is an autoregressive language model.
Yes.
And you give in your language the premises, the goal, and then the proof. It's that sequence, and it just completes.
Yeah.
Okay.
So during training time, we train the language model on this full string, and then during test time, we give it theorem and proof, theorem and conclusion, and then we ask it to generate the rabbit.
Right. Okay.
We have a raised hand from Abhishek.
Hi, can you hear me?
Yes.
So very inspiring work and very inspiring talk. And so this rabbit methodology goes very well with my experience doing proofs in the proof assistant for many years. And I also do a lot of inductive proofs, for example, proofs by natural induction. And you can think of the rabbit as the induction hypothesis. We often have to generalize the theorem that we are proving by induction. And so one place where the analogy becomes different from my experience of 10 years or more is that, like, when I come up with a rabbit, so I come up with some guess of what the proof, how to generalize the statement to prove it by induction, so-called the induction hypothesis, and then it doesn't work. Then the prover, like the cock proof assistant, by working to the proof, I see how it fails, and that gives me intuition about how to come up with the next iteration of the induction hypothesis. And that part seems missing in this work. And do you have some thoughts on how we can do this a similar thing in your approach?
Yeah, so this is indeed a missing part in our work, and in the sense that when we have a rabbit, and then if the proof fail, we need to feed back into the language model some information, which is not clear at all for us right now. What exactly is the information that is useful about this failure? So right now, just to make it clearer, the symbolic engine DDAR, what it does is building the deduction closure, which is all of the fact that it can generate. So one option here is to put this set of fact back into the language model. But of course, there's a practical issue here, is that this set of fact is too large. And if there's a way to compress this set of fact into like a short, a more compact representation. For geometry, maybe what we can do is to annotate the set of fact on a diagram, for example. Is also a good compact representation of this deduction closure. But we haven't tried that, but there are ways that we're thinking about.
Makes sense. Thank you.
Yeah.
Why don't you go on and say a bit about the interestingness?
Oh, okay. Yeah. We still have 10 minutes. So regarding interestingness, let me take you to a short story. Well, actually, after this paper came out, what I did is I looked on Evan Chen blog post, which is the Olympiad expert that do the manual evaluation of our work. So on the blog post, Evan would document the process that he came up with a new IMO problem. And here's the one. Here's the process. So Evan would start out by constructing some interesting diagram. So for example, this is one interesting diagram. We have some triangle and some circles. And then based on experience, Evan would add new points and lines that is conducive to giving interesting result, to make the diagram gradually more complicated over time. And then once we have interesting diagram, then Evan would make some deduction towards the interesting result. And then finally, once Evan have this interesting result, meaning, for example, these two lines are perpendicular, then the final step in proposing a new problem is to clean up the intermediate work and present a clean problem. So meaning hiding away all of the intermediate auxiliary points and lines that have been added to get to the result. And so the reason why I brought up this procedure is because this 4-step recipe is actually exactly like the 4-step recipe that we used in our work, except for the fact that we cannot capture the notion of interestingness. So we have no direction to construct the diagram, to make the deductions towards interesting result. So we ended up in our paper, we ended up doing a naive approximation of this procedure, where instead of starting with an interesting diagram, we start with a random diagram. And instead of adding new points that is conducive to interesting result, we add random points and lines. And instead of making deduction, only the deduction towards interesting result, we do the exhaustive building this full deduction tree. And then take everything as training data. And only the cleaning up the diagram is similar to the Evan-Chen recipe. So as you can see, what we're missing here is really a way, how do we even capture the notion of interestingness, and how do we operationalize or measure this signal so that we can be smarter in terms of generating these synthetic data. As it turns out, these naive approximations work for geometry, but we can easily imagine it would not work for other domains of math. For example, in number theory, if we were to do these random and exhaustive deduction, we might end up with theorems like prove that 1 + 1 = 2, and then prove that 1 + 1 + 1 = 3. And then we might have an infinite number of these examples that is not really interesting. But lucky for us, for geometry, these naive approximations allow us to still have a training data that is interesting enough to get good result. So everything come back to the question of what is interestingness. I don't have an answer. I guess this is an open research question, but I do have some pretty naive approximation of exploration of this question. So one of the things that we did is we get inspired again by the Fermat-Last theorem. What the Fermat-Last theorem, the reason why it is interesting is because with such a simple statement is hiding behind a large amount of complexity in order to prove that simple statement. And so trying to capture this notion of interestingness, we look at the 100 million synthetic theorems that we generated again, but this time, instead of looking at the problem with maximum proof length, we try to find the theorem with maximum ratio between proof length and the problem statement length, meaning we try to maximize the proof and minimize the simplicity of the theorem statement. And we ended up with a different theorem that looked like this. So what we did is we asked an Olympiad expert who have these experience in proposing problems at the IMO to evaluate this problem. And what we get is this is indeed an interesting problem, unlike this theorem on the left. And it's very hard to solve this problem without coming up with a rabbit. And maybe this problem can even be suited as an easier problem at the USA national round. So this might be some initial signal to follow if we were to capture interestingness. If we treat this problem of generate synthetic data as an RL problem, then this is probably a good signal to follow. But this is just a very preliminary exploration of this question. And that's it. This is the end of my presentation. Thank you.
Thank you. Questions from the audience? Any questions here?
I have a question.
Please.
In light of what you learned over the course of this project, what would you say about the role of mathematical intuition? Or mathematical.
The role of what?
Mathematical intuition.
Oh,
Many people would say that computers will never match humans in terms because they do not possess mathematical intuition.
I see. Well, I find it hard to comment on mathematical intuition in general, but at least in solving geometry, having these intuition clearly unlock a lot of results. So here is the evidence where DDAR certainly doesn't have any intuition in solving the problem. It's just blindly trying to build the deduction closure. But once we bring in the language model, we really have improved this result by a lot. So at least in Olympiad geometry, I would agree with that. But I don't have any, I guess, authority in commenting on general mathematics.
Jesse.
First of all, congratulations on this result. Super impressive work. So I wanted to dig a little bit deeper about the synthetic data algorithm for finding rabbits. So you mentioned that this is applicable to all sorts of domains of mathematics. I think it would be really cool to be able to find this in other domains of mathematics which are considered like deeper. Like, for example, are there like ways of synthesizing so like data for, say, graph theory, wherein like taking the spectrum of a graph is absolutely necessary for like an elegant proof? Have you investigated ways of selecting rabbits or finding rabbits which are somehow necessary for all proofs of some result, or perhaps rabbits which have like maximal power in terms of compressing all possible proofs of some result? And is there anything you can say about a formalization of this methodology in the language of mathematical logic, perhaps for like first order theories with like a certain number of function symbols, which are which have like an axiomatization that you pen to the theory? And finally, have you thought about applying this to, say, inequalities in the Olympiad setting? So which is another setting where it's like, so it's almost very standardized. There are plenty of function symbols around with finite axiomatizations that you can append onto the theory of real fields, and which are also a very standard part of the Olympiad repertoire.
Yeah, so I guess I tend to forget the long question, but let me try to answer the first question, the last question first. So we did think about applying this to inequality. I did definitely think this should be applicable to inequality. It's part of the, I guess, it's part of the experiment that we did try, but didn't push very far because I guess just too many work that is probably not necessary to submit this. But one thing that we did try to think about is how to generalize this work to many other domains of math at once. And we feel like applying generalizing to inequality alone seems to be a lot of specialized work that might not be worth it in the sense that maybe excelling at IMO problem is not that important or impressive. Second question, you were asking about whether to find domains of math where the rabbits is deeper in a sense. I don't know, but I did see Terence Tao commented on a Math Stack Exchange forum about the applicability of AlphaGeometry on a problem of on a certain domains of math that I don't remember, but it's about finding bound of some equation or some inequality. So definitely there's a chance to apply this to a research math that is beyond this just high school mathematics. I forgot the question in the middle. Can you repeat that?
I was asking if you've thought of a way to formalize this kind of technique in like more metamathematical language. Like perhaps you could somehow provide guarantees if you apply this to like a first order theory that has extra function symbols which are parameterized by like another finite axiomatization of each of the function symbols, which I think captures the scope of the work that's been done in geometry so far.
Would you say
because things like taking a midpoint can be could be viewed as like an extra function symbol, so which is parameterized by some relations to other points.
Would you say translating this work into the language of Lean a good answer to your question?
Not exactly, but
yeah,
but I think your answers are very helpful.
Yeah, I haven't really thought about that. I don't think I really understand all the terminology in your question, but we did have some attempt at translating this work to Lean that is ongoing. Yeah, I hope my answer is useful.
They have been, thank you.
Thank you.
Abhishek.
So let me try to ask Jesse's question in another way. Like, another way to phrase the question is like, if we take away the geometrical primitives and if this was an arbitrary list of function symbols, first order theory of arbitrary list of function symbols, and we take away the meaning, like instead of point, it's some arbitrary concept, would the same solver work if we abstract away the geometry and just consider it some first order logic with some function symbols and some accents about them?
I might not understand the consequence of abstracting away all the geometry primitives. I don't see any reason it's not this formula would not work, except for the fact that maybe we would ended up with a lot more uninteresting data to train on, which will end up being useless after all. For geometry, we're lucky in this sense. I don't know if that makes sense.
So the main claim is that there would be more useless data, more uninteresting data. Yeah. I mean, the definition of interesting is so vague, so that it's hard to judge that claim. So not sure, but thanks.
It does seem like, I mean, there is a close analogy. I mean, all your predicates and statements in your language could be phrased logically, but it does seem geometry is a much simpler domain in some sense, that introducing new points and edges and so forth is a much more controlled operation. I mean, certainly I think the intuition is for most mathematics. If you just try to generate random theorems in this way, they would be much less useful, but this was very useful. And I'll send you in a message. There are some interesting references on the Interestingness. I have a talk, and there was an old paper by Colton, Bundy, and Walsh, which is actually explicitly on this topic, which is quite interesting.
Yep.
Are there more? If not, let's thank Trieu again. Really great talk.
Thanks, everyone.
This is the last new technologies seminar of this semester. And in fact, we'll be doing things somewhat differently next semester, because there'll be a workshop here on math and machine learning in the fall, and the talks will be associated with that workshop. So I'll send around more information as those plans get made. So thanks to everybody for coming this year and for the past 4 years. Thanks again, Trieu, for a really excellent talk, and hope to see you all again before long.
Thank you. Have a good day, everyone.